Hello, everyone, and thank you for joining us today for this webinar entitled How ICME Enables Digital Transformation in Composite Manufacturing. It is brought to you by GEC Group and presented by e-Xstream Engineering, part of Hexagon Manufacturing Intelligence Division. My name is Benjamin Debucher, and I'm Program Manager for GEC Group. As manufacturing industries shift towards 4.0 post-COVID-19 to meet increased productivity and mass personalization needs, materials will play an ever more central role in successful products and businesses. The latest engineered materials come with a series of challenges, however, such as increased complexity, strong manufacturing performance interdependence, a need for significant material characterization or requirements around access control to proprietary or sensitive information. When it comes to composite material in particular, their full potential can be truly unleashed with the help of a material and process digital twin supported by integrated computational materials engineering, which is ICME. ICME is the full integration of processing microstructure property performance relationships at various length scales, wherein the linkages from processing all the way up to performance can be made and utilized to inform smart design and manufacturing decisions. In this webinar today, we will discuss how ICME applies to composite manufacturing application to deliver short and long-term value, and how ICME integrates in the digital transformation journey of the manufacturing industry and your business. Our presenter today is Philippe Hébert, Product Marketing Manager at e-Xstream Engineering. Philippe is a material engineer passionate about global challenges and, in particular, usage and impact of energy and resources in our 21st century economies. He has held various positions at e-Xstream Engineering across application engineering, product management, and now product marketing. Always with the same motto, help the industry make a smart use of material for a better future. This presentation will last about 45 minutes, followed by question and answers. So please feel free to share your question with us by typing them in the question tab on the right of your screen. There's also the possibility to upvote the question. In any case, we will answer all the questions at the end of the presentation. The webinar is being recorded, so you will be able to view the entire program later on geccomposites.com. Thanks again for taking the time to be with us today. I'm now going to hand over to Philippe. Philippe, it's all yours.
Thank you, Benjamin. Can you confirm that the sound is okay?
The sound is okay.
Okay, perfect. So hi everyone, and I join Benjamin to thank you for being with us today. So let's have a look at how ICME enables digital transformation in composite manufacturing. And first, let's have a look at what are the drivers in the manufacturing industry today. So there are many things that come along with the 4.0 era, like the industrial Internet of Things, lightweighting, which is all over the place in transportation industry, additive manufacturing and other digital-related manufacturing techniques, big data and AI, electrification, you name it. But one which we would like to emphasize especially on is also sustainability. And in the context in which we are today, sustainability takes a very special meaning, not only in terms of being sustainable on the environmental point of view, but also on the business perspective. And so what I'd like to show you today is how with ICME we can go in that direction. So if we start our journey by the sustainability thinking, it's basically all about having a full life cycle view on the products that we manufacture. So it means having a deep understanding of what happens starting from the raw materials, the design stage, the manufacturing step, having the product in use, and then once the product reaches its end of life, what happens next? Do we re-enter a new cycle, or what are the externalities that we need to account for? And having this point of view from both an environmental point of view, but also a cost perspective, is critical to manage the business right today and to manufacture better products. So this being said, if we want to have a full life cycle view, how can we do this from an industrial perspective? Well, we believe that the digital twin approach is especially required. So the digital twin is, in a sense, a representation of the reality, a different stage of the product life cycle, whether it's the R&D stage, prototyping, production, manufacturing, the product which has been delivered, which is maintained and then retired. All across these steps, what we want to do is have a digital description of the product and make smart decisions, smart measurements based on the gathered information. So obviously today we will talk a lot about the early stages once we are in design. So that means basically R&D here on this screen. But the big point to have in mind is that all the decisions that we will be discussing in the webinar today have a strong impact on the rest of the life cycle. So it's believed that 80% of the impact is mostly locked in the R&D stage. So it's essential to start right from the very beginning. And within the world of digital twins, we'll have a look today at what we call material digital twins. And these are descriptions of the materials based on their microstructure and providing a link to the manufacturing process. And this is supported by what is called ICME. So ICME, it stands for Integrated Computational Materials Engineering. If we have a look from a historical point of view, well, the material engineering context, it has been a lot about understanding the link between the material microstructure and the material properties. This is what has been done in universities since a while. But if we look at the meaning of integrated and computational material engineering, what it means is that first, to understand the link between the microstructure and the material properties, we use simulation techniques, which are now affordable with the rise in computational power. And integrated means that it goes all along the scales of the material, basically from atoms to the full structure. So in other words, it's the full integration of processing, microstructure, property, and performance relationships. And this ICME approach, it leads, we will see later on, to also an important aspect, which is the management of both physical and virtual data, and try to leverage on those two assets. So ICME, we tend to see it a lot from the technical perspective, meaning that we are defining an engineering workflow where the result of the manufacturing has an influence on the material, which has an influence on the part performance, which has an influence on the product business success. And from a simulation point of view, it's now very well addressed on how to link the various simulation softwares which are required to perform this. But I'd like also to emphasize that ICME is also some kind of organizational paradigm shift, because it means that you need to change the way you perform engineering. In the past, it has been a lot segmented into silos, where a designer throws a CAD with some given idea on what is the material, then we'll refine the choice of the actual material for the product. You throw that to a structural analyst, which finds some little tweaks to optimize the performance, and then you push it hard to the manufacturing guys who need to find a way to actually produce the part as it is. And so that's before. Now what we want to propose with ICME is to have an interconnected workflow where everybody influences each other, So it's much more interesting in engineering workflow that allows to find better overall solution. And that means that within engineering departments, we need to break the silos to have the designers talk directly with the material scientists, talk directly with the manufacturing guys, and with the structural analysts typically. So what does an ICME workflow looks like from a technical perspective? Well, ICME will usually involve different scales. So it means having a representation, whether from test data or from physics-based simulations of what is happening at the molecular level, then at the mesoscale level, at the coupon level, at the component, and then up to the final assembly. So that means that when performing an ICME workflow, one has to handle significant amount of data, which can either be simulation data or real-life data. And what I'd like to emphasize also on this multi-scale approach in terms of benefits is that there are really two big ways of applying ICME. One which is bottom-up and the other one which is top-down. So by going bottom-up, it's basically a cause-effect analysis. So by changing something at the lower scale, by applying ICME, you understand the consequences on the upper scales until the final product. And on the other hand, if you go top-down, what will happen is you can achieve a goal-oriented design method. So let's say you fix the desired performance by going down the scales and applying the constraints that you have for your design. You will end up finding what is the right material, what is the right microstructure, what is the right processing method to achieve the desired performance. And so that's how ICME is enabling this close connection between all the stakeholders that we were mentioning just before. Now, today we want to talk especially about composites. Today, in the previous slides, this was pretty much generic, so it would apply not only to composites, but to plastics, to metals, to foams, and you name it. Now, for composites, the typical steps would be to consider first what happens at the molecular level with molecular dynamics. So answers that we would answer at this scale would be, how does the chemistry improve my resin properties, for instance? That would be addressed to the chemist guys or material developers. Then going one scale above, we would be in the virtual compounding. We would look at questions such as what material microstructure should provide the desired properties, or if I need to increase my material strengths by 10%, what should I change in the way I actually compound my material? Then once the material actually exists, whether physically or virtually, we need to understand precisely how it's handles during the manufacturing and have a look at what processing conditions enable high quality components. So high quality, it means obviously the final part shape. It means also the final material properties that we get once the part has been manufactured. Then moving forward and going towards the creation of a final product, we can address also virtual coupon testing. That means performing from a purely simulation standpoint, all the coupon testing that would happen in a lab. And as we all know, when we manufacture composites, there are usually defects which are introduced and which have an impact on the material properties and which require to define knockdown factors. And these knockdown factors, we can very precisely estimate them from simulation of the virtual coupon, where we introduce the exact defect that we want. And we'll have a look at this later on in an automatic fiber placement case. And then finally, the upper scale is kind of the holy grail in this workflow, where we can perform full-scale damage analysis, accounting for all the details that have been mentioned above, meaning that we can answer the questions such as what product performance can I reach, and how can I actually reach it by collaborating with the chemist guys, with the material scientists, with the manufacturing guys, and so on. What I want also to show you in this composite ICME workflow is that at each step, we have both a simulation approach, which is to predict what can happen, but then we also have a data management aspect, which is very important to capture on one side the simulation data which is generated and which can be especially large for composites, but also capture the real world data, the experimental data, which can be used to feed simulations or to validate the simulation results. And what happens when we go for an ICME approach is that we will start playing around with both this physical and virtual materials data along the composite value chain. And by having both these data, we can feel that there is an opportunity to blend those data together and to build more from what is available. And that's what I would like to show you in the next few slides as a starting point. So first, let's have a quick look on what material simulation can achieve for composites. So here is an example where we simulate the response of unidirectional composites with an epoxy combined with carbon fibers. From a simulation workflow perspective, it means describing the behavior of the polymer matrix, of the carbon fibers, the characteristics of the interface, and then defining the composite architecture. So what is the fiber content, for instance, what is the fiber orientation, for instance, for this application. And once this information is defined, what you can expect as outcome is basically any kind of mechanical testing on the material. And that means we can go beyond the classical physical testing, which is usually uniaxial, hardly biaxial, because it's very complicated. But here with simulation, it's the same cost to do a biaxial testing or a uniaxial testing. And what you can see on the graph here is what you would get experimentally without a simulation approach would be these three orange crosses. With simulation, you can get that same information, and in addition, also what happens for more complex load cases. So that means you can access more materials data and improve your understanding of what is happening with the material. If we go as one scale above at the composite coupon level, then we will start talking about virtual allowables. So replicating the full allowable generation process, but through simulation. And to do this, we need to have a few technical ingredients that I show you on the slides on the left side here. So at e-Xstream, we've been working a lot on this topic over the last few years. And we've also partnered with the University of Porto to develop the best failure models. And what it means from a result perspective is that for classical aerospace composite grades and different kinds of layups, we are now able to predict the strengths, whether for unnotched or open hole coupon in tension and compression, with an accuracy of plus minus 10%. And we believe that this is really a requirement to then push that virtual data further. So let's have a look now at two use cases. One, which is how ICME for composites can be applied to reduce the cost of materials data. And then we'll have a look at another case, which is around novel manufacturing techniques, let's say, and automatic fiber placement. So first, let's start with reducing the cost of material testing. So this is obviously a very important concern for anyone who needs to manufacture composite parts. For the design stage, we need to know what material properties we should use to design the part. And accessing those material properties usually require testing. And for composites, especially due to the high number of variables that you can have, that testing phase can become very expensive, whether from a time or cost perspective. And the good news is that there are ways now to accelerate the development cycle here with the digitalization of material testing. So there are three big concepts that become mature enough now, and they are the ones that we saw in the beginning. So first, virtual material development, understanding how the combination of different constituents can generate the desired material properties. We have virtual testing, which is the coupon testing that we mentioned before. And then also the materials data management, which is becoming more and more standards across enterprises. Data management may seem quite obvious, but it's a strict requirement to capture all the data which is generated inside a company, whether it's a physical or virtual data. And once you have these three building blocks in your methodology, you can start creating some interesting data workflows. So from the first two methods, what you get as outputs typically are virtual material data, which are based on model predictions. Okay, so it's all the physics that you have in the simulation models that drive your virtual data. From the data management perspective, what you typically get as output is physical data. So the tensile test that you perform on day X with the test machine Y and the test operator Z, you can retrieve it directly from this data management. But once you have these kind of data outputs, what becomes interesting with the rise of artificial intelligence and smart data management techniques is what you do out of it. So with the model-based virtual data, when we apply a layer of artificial intelligence, we're able to speed up significantly the simulation time. And when we apply artificial intelligence to physical data, what we are able to do is find new data points based on physical data, but which has not been tested in the real world. So that's why we call them physical data based on virtual data. So no, sorry, it's physical data based virtual data. So it's becoming a bit of a mess. But in the end, once you have these faster simulation models, once you have your virtual data based on physical data, you can also combine them together towards what we call hybrid data. And we'll actually show you an example of this right after. So if we want to make this vision a reality, to combine physical and virtual data, we need to have a good framework. That means having a materials data management system inside your company, which is able to capture both the physical and virtual data at the different scales. So information about the constituents, information about the architecture of your material, information at the ply level, information about how panels and specimens have been manufactured, and then having the right connectors between each and every scales, whether from a simulation perspective or simply from a data management perspective. So let's have a look at two scenarios that apply this framework. And let's have a look now on how we can create value from the large amount of both physical and virtual data available in the company. So to do so, what we want to do is first collect all the available information. And if you have already a material data management system, well, the homework is done, everything is there. And what we will do from from there is train a model with something like 100,000 data points, which for the record is worth approximately millions of euros. And by having this model, we'll be able to find information about new composite combinations, so layups, testing conditions that have not yet been tested. Okay, so step one, like we mentioned, is to gather the material data. Here, what we have done in the following exercise is perform something like 15,000 simulations. So it's approximately 42 days of runtime. We looked at 4 different UD material systems, 4 types of coupon tests, so unnotched and open hole tension compression, 960 different stacking sequences, which were symmetric and balanced, and we kept to the room temperature dry conditions. On top of this, we added 56 experimental data points from the literature, so only 0.3% of the simulation points. And with this, we started training the AI model. So first, what we do is that we train an AI model with solely the simulation predictions. Okay, so what you see on this graph is only the case of unnotched tension strengths for the different kinds of stacking sequences. The orange points are simulation results, and the green points are what the trained AI model is able to predict. And so what you see is that an AI model is able to replicate pretty well what you get from the simulation. But at this stage, what we haven't done yet is include the value of the experimental data. And so this is actually the next step. So now that we have an AI model which has been trained on the simulation data, we will train it on top with the physical data. What happens here is that the AI model fidelity is improved when we train additionally with physical data, because we are able to capture what is happening exactly in the real world. And in this case, we took a kind of tricky combinations for the simulation models, which is the deploy bunching effect, which was not present in the simulation model that was used. And what we see is that once we include the experimental data in the training of the AI model, which is here in purple, it becomes much closer to the experimental data. So overall, once we apply artificial intelligence to virtual and physical data, what do we see? Well, we see that from an experimental perspective, we have a strong influence of the applied bunching effect. The initial simulation data points do not capture the effect of bunching because they were not yet using the ingredients that I showed you before. And once we start training the machine learning model with both simulation and experimental results, we have better average values, but we are still not able to perfectly capture the effect of bunching because the first machine learning model did not actually capture this effect. So long story short, what do we need? Well, we need to have a simulation model which has as much physics as possible. And good news is that now it's actually possible with the latest releases of the virtual testing software from our ICME platform. And we need to include more experimental values to train a machine learning model. So if you are interested to join this effort, you also are welcome to contact us afterwards. The second scenario on the combination of physical and virtual data is the following one. It's how we can use virtual data to complement and optimize physical data needs. So here we will not be looking at artificial intelligence anymore. We'll simply look at simulation as a decision helper for better testing in the real world. So if we compare a 100% physical approach with a hybrid approach. If we want to develop a carpet plot, what will we see is that, well, from a physical perspective, we need to combine all layups, time all types of tests, time all repetitions that are needed to capture the variability. And this will be required to meet the desired material data. And with a hybrid approach where we can start with simulation, what happens is the following. So you perform first simulation based on a very limited set of physical data, like laminar information. This gives you an indication of the best candidates from the virtual data results. And from the good candidates that have been identified, then it becomes possible to perform only physical testing for those ones. That means that the blue arrow that you see here, which represents the time and effort needed for testing, becomes really reduced, because instead of testing all possibilities, you test only the right candidates that were suggested by simulation. And obviously the gap that you have between both is the time and money which is saved. Okay, so this ends this first part of the webinar, where we looked at how ICME can lower the cost of materials data, whether with artificial intelligence, whether with, let's say, design decisions which are guided by simulation insights. Now, I'd like to go a bit more into the actual manufacturing stage in the engineering workflow, and talk about novel manufacturing techniques where ICME can also have a significant role. And today we'll have a look especially at automatic fiber placement. So automatic fiber placement, also called AFP, it has been, as you may know, an answer to one of the main aerospace challenges, which is to integrate more composites materials in aircraft. And one of the driver is, of course, the production rate. So it's estimated that with automated manufacturing processes such as AFP, we can be something like 20 times faster than hand layup. So how does automatic fiber placement work? Well, this is, as you can see, an automated manufacturing technique, which goes hand in hand with the digitalization topic, obviously. And so what we have is tubes of material, which are usually fibers that are pre-impregnated and are deposited following a discretization of the part geometry that we want to reach. And so as part of this discretization, what happens is that we cannot perfectly cover the desired geometry. To do this, we would have to have very, very narrow material strips, and it would not be possible from a physical perspective. So as engineers, we need to live with the defects that are introduced by the process. Hopefully there are defects that we can predict quite easy, because it's already an information that we can extract from the manufacturing software that allow to prepare this kind of processes. So we'll be looking in the next slides at understanding better these defects, mainly gaps for today. So as you can see in this cross section, when you have parts of composite material which are not present due to the defects, this will introduce either a reduction locally of thickness or a reduction of the fiber volume fraction. In any case, this will affect directly the local material properties and have an impact on the actual real part performance. And this means that once we start introducing automatic fiber placement in engineering workflows, it means we need to revisit also the traditional design methods, because with these automated manufacturing techniques. We have defects that are introduced and that need to be characterized. And hopefully, since those defects can be also quite well controlled, we need to understand what are the right trade-offs in terms of how wide can be the gap, how should they position compared to a hole that is in a part. And this means that new approaches are needed across the scales, starting from the coupon level to the elements and then to the final components, which are all impacted by the defects and gaps. So if we start from the lowest scale that we show on the previous slide, we first want to have a look at the coupon level to understand the effect of defect location on the coupon strengths. And this is something which is made possible with a virtual allowable approach, where the workflow is the following. So you first define the defect characteristics and the location. Okay, so things like the gap between courses, the transverse shifts, the location versus the hole, and so on. Once this is defined, it's all about simulating correctly the local material properties due to the modification of the local microstructure. So in this example, in the gaps zone, what we have is a lower amount of fibers. That means that the material will be less stiff and will also be less strong in those areas of the ply. And the question is, once I perform a tensile test on this coupon, what is the knockdown factor that I get? And with the simulation approach, you can compare what happens from a pristine point of view, so without any gaps, and when you have the defined gaps, what is the final strength? And this knockdown factor can then be evaluated for all possible defect variations and can enrich the final decisions on how to manufacture the part. Okay, so in summary, this virtual testing approach, it helps to virtually investigate any scenario of the toes deposition with the possibility to consider gaps anywhere in the laminate. So there is strictly no restriction there. And if you want to do this purely in a physical way, as you can imagine, it can become a significant effort because you need to test all possible combinations. So now moving on to the full parts, what we'll witness are the same challenges. So from the manufacturing process point of view, we will know where is the fiber and where are the gap locations, which is a very important aspect because it will drive the local material properties. But also on top of this, we need to know precisely what is the local fiber orientation, which can vary because it's following the actual parts geometry. And so to have an accurate prediction of the part's performance, we need to have this intermediate step where we look at the as manufactured composite characteristics. And to have this information, it's all about transferring those manufacturing data and having a multi-scale material modeling approach so that in the end we can predict what is the level of stress that we have locally as a function of the real microstructure. In summary, at the component level, like the wing that we have here, the connection with the manufacturing process is really crucial because it enables, on one hand, to transfer the exact location and shape of the gaps, and on the other hand, the as manufactured fiber orientations, which can change versus an idealization of the part. And with ICME, we have an integrated method to address those two challenges and truly connect the process with performance through the material model, which is sensitive to the microstructure. And where is this leading to? Well, up to now, we have mentioned only the designed manufacturing, in the sense that it's the programming of the machine that we are using to feed the defect information. But obviously, when it comes to manufacturing, there is perhaps a difference between what you ask the machine to do and what the machine has actually done, because there can be variations between what you plan and what actually happens. And so this approach, where we connect the manufacturing with the material microstructure and the part performance, it leads naturally towards a digital twin of a full AFP structure, by adding on top of the digital world also real-world information. So in the real world of manufacturing, with deposition techniques, we can capture with scanning real-time information about the ply orientations, about the defect locations. And this enables, therefore, to connect that information to a digital twin of the AFP structure and evaluate on time the impact of any defect that has been introduced, or any difference that has been introduced between the machine programming and the real world data. So this being said, key takeaways for today: why ICME for composites? So first, support the need for more composite material data at an affordable cost, connect all stakeholders with a material digital twin for improved collaboration, manage complexity of composite material design variables, accelerate the adoption of new manufacturing technologies like fiber placement or additive manufacturing, reduce the risk by anticipating manufacturing issues and effect of defects, and finally, improve production rate thanks to better control of the manufacturing process. And with that, I'd like to thank you for your attention. If you want to learn more about ICME, we are happy to welcome you at our ICME conference, which is taking place beginning of October. You will receive the link in the webinar environment right now. And I'm happy to take any questions that you have.
Thank you, Philippe, for this really great and insightful presentation. I can see that attendees just received the message about the ICME conference. So we don't have questions for the audience yet. Maybe we need to leave them a bit of time to digest the presentation and prepare their question. So again, please continue to type your question in the question tab on the right, and Philippe will answer all of them. So really don't hesitate to submit. In the meantime, Philippe, I have some question for you. So my first question would be, do you think that the virtual data can replace the physical data?
So thanks for your question, Benjamin. Well, I think that point was partially addressed in the presentation today. So it's always a matter of understanding the value of the data that we have, and what we believe is that virtual data is acting not a replacement of physical data, but more as an advisor on what should be the best data point to test physically. So it's a way to reduce the amount of physical testing to only what is really required, but it's not going to replace 100% of the physical data.
Okay. Okay, so maybe I have another question for you. How accurate can the composite failure predictions be, whether at the material or coupon level?
So that's a pretty important question, obviously, because it drives the fidelity and the level of confidence that we can have in the simulation responses. Today, what we can achieve, and that's what we saw in one of the slides very quickly, at the coupon level, for instance, is something around 10% of difference between the physical and virtual data. I don't think that we can, that it's wise to start digging further, because then there can be quite a few differences between the digital and the physical world that are really hard to address. Like, how sure are you of the quality of the physical measurement that you have? How sure are you of the actual microstructure that you had in your real sample and that you try to replicate with the virtual approach? There are many factors that will always lead to a difference between physical and virtual data. But now I think that we have the right physics and we have the right computational tools, especially to have something like a 10% level of accuracy.
Okay, still waiting for. Sorry?
I hope this answers the question.
Yeah. Still waiting for some question for the audience. So maybe for those who want their organization to adopt ICME, what would be your advice for them to motivate their organization to adopt such technology?
So to me, my advice would be to remember that ICME is not only a technical. It's not just a technology. It's also something that brings a different way of envisioning engineering of materials, especially. So it means that we need to first understand the benefits and find a project where ICME can bring value, and then gather all the stakeholders around that project, and make sure that everyone is on board, is able to collaborate. That means that the people from manufacturing are able to provide the information which are needed, the people from materials and processes as well, and so on, and that there is a framework to connect everyone together. So that would be my advice. So find a relevant project and make sure that the people are on board and connected.
All right. Thanks for your answer. So I think the audience is too shy right now to ask you a question. So I would like to thank you again, Philippe, for this presentation and for answering my question. I would like to thank our attendees today. If you have any question that come to your mind after, or if you need information about ICME and e-Xstream, please do contact Philippe. This webinar has been recorded again, as mentioned at the beginning, so you will be able to view the entire program again after on GECComposite.tv. So the next JEC Composite webinar will be held on October 6th, from 4 to 5 p.m. CEST, and will be about thermoplastic honeycomb sandwich panel technology, meeting the cost efficiency and sustainability targets with Thermex and EconCore. So check the details on GECComposites.com if you wish to register. And we appreciate again everyone's participation today, and we hope to see you again soon at the next JEC Composite webinar. Have a great day, everybody. Thanks again, Philippe, for your participation, and see you next time.
Thanks, everyone. Bye-bye.
Bye-bye.